Hello class, these are our notes for sections 519 and 520. So for section 519 in Algebra 1, we're looking at which one changes faster. So suppose that you won the top prize from a game show and are given two options. The first option is a gift of $10,000 and $1,000 per day for the next 7 days. The second option is a cash gift of 1 cent that grows tenfold each day for 7 days. Which option would you choose? So they're giving us a little chart here that we can work on filling out. So option 1, that's the one where we get $10,000 right away, $1,000 after that. So I feel like at the top of this, I might want to write what's going on at the beginning, right? So my f of 0, so at time 0, I have $10,000. Okay, and then I get another $1,000 each day for 7 days. So let's see, if I add $1,000 onto that, day 1, I would then have $11,000. Day 2, I would have $12,000. Day 3, I would add another 1,000, so I'd have $13,000. And then I can kind of see a pattern here where, like, because it was a 1, I added 1,000, a 2, I've added 2,000 so far, 3, I've added 3,000 so far. So I can even fill in the 6 and 7 right now. So at the end of day 6 or after day 6, I guess I'm not sure how we word that, if you get the money at the beginning of the day or end of the day or however that works. But I have 16,000 and then 17,000. So I think I could write an equation for this. So I start out with $10,000, but this isn't exponential. I'm not multiplying each time, right? I'm just adding. So if I'm adding something each time, that's when we're looking at a slope. And so for every day, I get an extra $10,000. That means my slope would be 10,000. And so I'm adding 10,000, or sorry, 1,000. So I'm adding 1,000 times my number of days. And those number of days are going to be x. So 1,000x. And this works. If I put in a 3, for example, it's 10,000 plus 1,000 times 3, right? So that's my linear equation. So the first option is linear. The second option, I start out with only 1 cent. So for the first day, I have, for the first day, I would have one, I guess G0, right? That would be 1 cent. And then for the first day, if I'm multiplying 1 cent by 10, so that's what tenfold means, right? Tenfold means I'd multiply by 10. That still seems like that's not going to be much money though, doesn't it? So 1 cent multiplied by 10, now I have 10 cents. Okay, multiply 10 cents by 10, now I have $1. Multiply $1 by 10, now I have $10. It's still a little bit worrying, right? So let's see, 4 would be 100. 5 would be 1,000. I just keep adding zeros. Okay, 6 would be, what would 6 be? 6 I can put over here. So 1,000 times 10, okay, that's going to be 10,000. This is actually growing a lot faster than I thought. And then 10,000, if I multiply by 10, I'm adding another 0 again. So it's 100,000. So definitely option 2 is going to be the one that gets us more money. But man, starting out with just 1 cent, it's crazy when you have a big multiplier, right? When your growth factor is a big number like that, how quickly your amount changes. So let's go ahead and write an equation. So I know I keep talking about how it's our starting amount times our growth factor to whatever power. So our starting amount here was that 1 cent. So we have 0.01. And then times our growth factor. So our growth factor here, we kept multiplying by 10, so that's going to be 10. And then raised to the x power. So if I was to say put 6 in there, and I worked it out, I would get 10,000. Make sure you know how to use a calculator if that's necessary. And for a lot of these problems it is. I'm seeing that in my classroom, that you understand when I do a problem, but being able to get the right answer on a calculator without multiplying over and over and over again, right? That's the issue. We want to be able to use exponents on our calculators. So next we're looking at 520. We're also comparing linear and exponential functions here. I mean, we look at this one right here, that's a straight line. Right away we can tell that that's linear. That's literally what linear means. It means when you plot your points, you have a straight line. And this looks a lot like the exponential functions that we've been working with as well. So let's read what this says. Linear and exponential functions each behave in a particular way every time their input value increases by the same amount. Take the linear function. So remember linear, I said like a straight line. Remember linear is y equals mx plus b. Or I think I did it a little bit backwards up above, right? Up above, I wrote my b part first and then my mx part. And I think that's a lot because we've been talking so much about start times growth factor. I really like the idea of writing the start first on that one. It's the same thing though, we're just reversing the order. It's defined by f of x equals 5x plus 3. So remember 3 is my y-intercept. That means I start it at 3 on my y-axis, right? And then my slope 5 means I'm moving 5 up, so up 5 and then 1 to the right. So my vertical change is 5 and my horizontal change is 1. So my slope is 5, and that means for every 1 unit I move for the right, I'm going up 5. So let's write 5 over 1. So as x increases by 1, my f of x, or my y value, right? I don't care what you call it here. So here's y. Y is the same thing as f of x. So I'm going to write that f of x increases by 5. So when we have you guys graph something like this, often what we do is we take a point and we say, all right, count up 5. 1, 2, 3, 4, 5. And then we have you count over 1 and we make that steep vertical looking line. I know it doesn't look very steep here, and that's because of what the scale is, right? It looks like my x scale is going up by 1s and my y scale is going up, I'm not even sure, by 10s. So it's hard to tell depending on the scale. But we can see right here where they have the 1 and the 5 here to kind of show us that slope. So as your x increases by 1, your y is increasing by 5. The graph starts at, well, it starts at the y-intercept, and we already said the y-intercept was at 3 on the y-axis, and so as an ordered pair, that's 0, 3. That's going to be our y-intercept. Now let's look at an exponential function. So we had linear, now we're going to look at exponential. And this is the function g of x equals 2 to the x power. So I know we always talk about start times growth factor raised to the x power. So let's remember, if I had to rewrite that, so it'd be in that format, I would have 1 times 2 to the x power. So just because there isn't a number there doesn't mean that it's not like a 1 or something. So sometimes we have to think. So each time x increases by 1, well, what's happening? So if I go from 3 to 4 or from 4 to 5, what's happening to those y values? Well, my y value is going from 8 to 16. My y value is going from 16 to 22. So it is doubling, and that's because the growth factor is 2. A growth factor of 2 means it's a 100% increase, right? My new value is 200% of the old. So each time x increases by 1, the value of g of x doubles. And then we're going to make a little note here that that is our growth factor. It's not our growth rate, but it's our growth factor. And I'm almost writing the wrong one here. Growth factor. Got to be careful about talking about one thing and writing another. Oh, my pen is not really wanting to cooperate right now. All right, let's just switch colors. Not sure why blue wouldn't work, but green will work. The value of the growth factor. And the graph starts at, well, because I have a 1 right here for my start times growth factor, it starts at 1 or, of course, 0, 1. So that's kind of like my y-intercept. So if I wasn't sure, if they didn't give me an equation, remember a way to get that growth factor too is to take these y values and make a fraction out of them. So take the ratio. So 32 divided by 16, well, that's 2. Or 16 divided by 8, that gives me 2. So if you only are given some data and you know it's exponential, you can still find a growth function or a growth factor. And that's because my function's going from 4 to 5, right? I have to take 2 that are in a row. So now we're filling this out at the bottom. So a linear function always increases or decreases by the same amount over equal intervals. And with linear, we're thinking like add or subtract, right? We're adding an amount over and over again or subtracting amount. So increases or decreases, but I really want to write like plus or minus. An exponential function increases or decreases by equal factors. So we're multiplying or dividing by something here. And really, when we divide, we're multiplying by a fraction, right? If I'm dividing by 4, I'm really multiplying by 1/4. So when we talk about exponential, we want you to think about how we're multiplying something each time. So linear, adding and subtracting. Exponential means we're multiplying by the same thing over and over and over again. Those are really some key ideas for this unit. So big ideas today are just kind of comparing how linear and exponential functions grow. Can you look at it in a table? Can you identify when you've got linear and when you've got exponential? So remember in this first one, they didn't tell which was which. We had to recognize that the first one was linear because we were adding 10,000 or adding 1,000 each day, and the second was exponential because we were multiplying by 10 each day. So that's how we figured that out. And just this idea that we can look at the graphs and we can compare what a slope is and what a growth factor is. So as always, class, if you have questions, please make sure you ask.